Satellites gone up to the skies. Things like that drive me out of my mind.
Phytoplankton are single-celled photosynthesizing organisms that exist in the euphotic zone. Deep genetic diversity has ensured their survival despite considerable changes in the Earth's climate. Environmental stresses have proved to be evolutionary selection mechanisms which create diversity and stability within populations. Whilst it is clear that phytoplankton help regulate atmospheric carbon dioxide, changes in phytoplankton populations are a consequence of poorly understood climatic feedbacks. The advantages of remote sensing over conventional oceanography are clear. Satellites sample over a greater spatial scale than is possible with ships, and at frequencies that are impossible to match by any other sampling procedure. Empirically, phytoplankton production per unit area of the sea surface is a linear function of surface insolation. The first satellite used for measuring global chlorophyll levels was the Coastal Zone Colour Scanner, which launched in 1978 and clearly demonstrated the feasibility of measuring phytoplankton pigment from space. In 1997, the Sea Viewing Wide Field of View Sensor, (SeaWFS), was launched on the OrbView 2 spacecraft, which viewed the Earth in 6 bands of the visible spectrum. SeaWFS used the Ocean Colour Empirical Algorithm OC4V4, which quantifies chlorophyll as a function of how much blue and green light is reflected from the sea surface. A simple ratio of blue light at wavelengths of 443, 490 and 510 nanometers to green light at 555 nanometers is used. The Moderate Resolution Imaging Spectroradiometer, MODIS, was launched in 1999 on board the NASA Terra satellite. It had more wavebands, a higher SN ratio, more complex onboard calibration, and was also able to simultaneously observe ocean colour and sea surface temperatures. A further MODIS on the Aqua satellite was launched in December 2000, providing 2 observations per day. Certain problems arise with the remote sensing of primary productivity. Globally, the sampling bias is larger than the natural interannual variability of chlorophyll. The most widely used empirical algorithm can be in error by a factor of 5 or more due to differences in the backscattering properties of phytoplankton and the related concentrations of coloured dissolved organic matter and minerals. It is assumed that low productivity regions have small phytoplankton, whereas upwelling and nutrient-rich zones contain larger, bloom-forming organisms. However, in a changing climate, phytoplankton composition may also change, and organic matter and mineral concentrations may become uncoupled from phytoplankton stocks. The current algorithm is only effective when conditions are similar to the present and small phytoplankton populate the oligotrophic ocean. However, when considering the changing ocean, the backscattering and adsorption properties of various types of phytoplankton and other compounds across the visible spectrum should be accounted for. In the modern ocean, photosynthetic carbon fixation by phytoplankton leads to the formation of 45 gigatons of organic carbon every year, of which 16 gigatons are exported to the ocean interior. Changes in the fate of organic carbon will strongly influence atmospheric CO2 levels, and hence climate, on geological timescales. Because the average turnover time of phytoplankton carbon in the ocean is so short, it is extremely sensitive to external forcing and consequently is seldom in a steady state. The global distribution of phytoplankton is defined by the availability of light and nutrients, which are in turn regulated by physical oceanography, atmospheric deposition, and the solar cycle. The link between the physical environment and ocean biology functions through changes in upper ocean temperature and stratification, which in turn influence the availability of nutrients. These physical factors, most of which can be measured by remote sensing, were combined by Berenfield et al. In 2006 into an index for evaluating the strength of El Niño and the southern oscillation cycles. Because strong ENSO events have major impacts on phytoplankton and are striking examples of climatic influences on ocean biology. Certain decadal climate trends have been found to influence primary productivity. Martinez et al. In 2009 used data from the SeaWFS satellite to find that multi-decadal changes in phytoplankton abundance are related to basin-scale oscillations of the physical ocean, specifically the Pacific decadal observation and the Atlantic multi-decadal oscillation. The observed changes in phytoplankton over the past 10 years are likely due to basin-scale oscillations in the physical environment. These oscillations can alternately weaken or emphasize the effect of global warming, making it difficult to identify the trends over short timescales. Resolving the changing properties that influence oceanic primary production over time will require improved accuracies and significant expansions in the spectral range and resolution of future remote sensing measurements. Almost all coupled ocean-atmosphere climate models predict that the mean temperature of the Earth will increase. This will be accompanied by increased heat storage in the surface ocean, generally enhancing stratification at all latitudes. Such a scenario predicts a decrease in the effectiveness of the biological pump and potentially contributes to a net efflux of carbon dioxide from the oceans to the atmosphere. That is, a positive feedback. Only the remote sensing of oceanic primary productivity can provide data that is sufficiently widespread enough to keep track of total global change. The future of the remote sensing of primary productivity will include active sensing, such as light detection and ranging, which could probe the depths of the oceans. Estimates of integrated primary productivity could be dramatically improved by incorporating the vertical distribution of phytoplankton in the water column. More comprehensive and consistent field observations could be provided using measurements from ships, moorings, gliders and profiling floats. This should help eliminate the perennial problem of cloud cover that arises because ocean colour can only be measured from space when clouds are absent, but higher chlorophyll measurements are associated with clear skies, creating a bias.
Satellite of love, satellite of love.